So section 6 is really telling us all about how that mean and standard deviation give us a lot of information about the distribution. We don't even need to see the drawing or the display because the mean and standard deviation through two different rules, Chebyshev's rule and the empirical rule, tell us pretty much what's going on with our data. So Chebyshev's rule works regardless of distribution. So even with skewed data, the percent of data that falls within a certain number of standard deviations follows this rule. Now this is a rule I will never ask you to calculate, but I do like the idea of sort of understanding that we know how much data falls within a certain area, a certain range of data. So 2 standard deviations above and below the mean is something you could look at. Even with something that might not be normally distributed, IQ scores are generally thought to be normally distributed, but even for something that wouldn't be, Chebyshev's rule would say that at least 75% of our data will fall within 2 standard deviations of the mean. So you actually have a cute little graph here that shows you within 2 standard deviations, you have 75% of the data, and within 3 standard deviations, you have 89% of the data. So the majority of observations are going to be within 2 or 3 standard deviations of the mean, whether we're dealing with symmetric or skewed data. The empirical rule lets us get a lot more precise with this. In the case of normally distributed or approximately normally distributed data, and just as a heads up, we did talk about this briefly, but approximately normal would mean unimodal, symmetric, and with that bell shape. So if our data fits this particular set of criteria, then we actually know a little bit more data falls into each of these ranges, right? So for Chebyshev's rule, 2 standard deviations was 75. Now we're up to 95% of the data. And 3 standard deviations was only 89 with Chebyshev's, and now we're over 99% of the data. So definitely gives us a whole lot of information about where the majority of people fall. So this empirical rule, we will have to know. Chebyshev's just the general feel of it. And the empirical rule you can do with these type of example questions. So the weights of adorable fluffy kittens are normally distributed with a mean of 3.6 and a standard deviation of 0.4. Draw the normal curve representing this distribution using the empirical rule. So what we would do here, this is where we hope I can do simple math in my head. I'm going to make a really fat normal curve so that way we can fit everything. Our curve is going to be centered at the mean. So our mean, they told us, is 3.6 pounds. And then we want to go 3 standard deviations above and below that mean, just like Chebyshev's rule. So 1, 2, 3. Well, those should have been better spread out. I'll do that again. 1, 2, 3. 1, 2, 3. All right, and then, like I said, these are just standard deviations. To the right, we're going to add standard deviations. So since my standard deviation was 0.4, I'm going to add 0.4 again and again until I get 3 standard deviations above. And I'm going to do the same thing in the other direction, except for there I'm going to subtract standard deviations. And then the empirical rule is also known as the 68, 95, 99.7 rule, but that can be a little bit hard to work with if I give a test question about it. So sometimes it's easier to have just these inside probabilities that I mentioned on your note card. So we're going to fill those in. 34, ooh, I wanted a different color. 34%, 13.5%, 2.35%, and 0.15%. And it's the same to the other direction as well. So 34% in the middle, 13.5%, 2.35, and 0.15. And this makes sense because in a normal distribution, the majority of our data is centered right around the mean, right in this bell shape. So you can see there's a lot more going on within that first area than in the next subsequent areas. So the questions that would come up from an empirical rule question look like this. Find the probability that a randomly selected adorable fluffy kitten would weigh more than 4.4 pounds. So always has to be based on one of our cutoffs, and then more than 4.4 would be this area, and we're just adding up all the percents in that particular area. So that's it. 2.5% chance that an adorable fluffy kitten would weigh more than 4.4 pounds. Then I could ask about any of these different ranges. I could say between 2.8 and 4 and all these different things. And it's just all about figuring out which sections we care about and then adding them up. So I'll go ahead and make a second video for the other one, but I say just try it on your own, see how you do, and then check the answers after.